Subscribe so you don't miss out on any of these videos. Stars, the luminous spheres of plasma held together by gravity, have fascinated humanity since the dawn of consciousness. The sheer number of stars in the night sky, their seemingly infinite variety, and their mysterious nature have sparked the imagination of cultures across the world. At first glance, stars may appear as mere pinpricks of light in the cosmos, but their significance is monumental. These distant, radiant objects are not only fundamental to our understanding of the universe, but they are also the forges where all the elements that make up planets, life, and everything around us are born. The life of a star is defined by a delicate balance between the opposing forces of gravity and nuclear fusion. In its core, a star fuses hydrogen atoms into helium, releasing immense amounts of energy in the process. This energy, in the form of heat and light, counteracts the inward pull of gravity. But as we delve deeper into the intricacies of a star's life, we realize that this cosmic equilibrium is fleeting. Stars are born, live their lives, and die, often with violent and spectacular conclusions. Their life cycle is one of the most fundamental processes that drive the evolution of galaxies and the universe at large. Stars are born in vast, cold clouds of gas and dust known as molecular clouds or stellar nurseries. These regions, often called nebulae, are the birthing grounds for countless stars. The process begins when a portion of the cloud experiences a disturbance, perhaps from a nearby supernova or the gravitational influence of another stellar body. This disturbance causes the gas and dust to collapse under its own gravity, and as it contracts, the material at the center becomes denser and hotter. Eventually, when the core temperature reaches millions of degrees, nuclear fusion ignites, and a new star is born. But not all stars are born equal. The mass of a star at its birth determines its entire future, dictating how long it will live, how bright it will shine, and how it will ultimately die. The most massive stars, sometimes over 100 times the mass of our Sun, live short, intense lives, burning through their nuclear fuel at a rapid pace. These stars shine with blinding brightness, sometimes millions of times more luminous than our Sun. However, they may only live for a few million years before exhausting their nuclear fuel and meeting their explosive ends as supernovae. On the other hand, smaller stars, like red dwarfs, are far more common in the universe. These stars, which can have as little as a tenth of the Sun's mass, burn their fuel much more slowly. While they are dimmer and cooler than massive stars, red dwarfs can live for trillions of years, outliving many of their more massive cousins by orders of magnitude. In fact, some red dwarfs born at the dawn of the universe may still be shining today, with the potential to outlast the universe itself. The fate of a star is intricately tied to its mass. As a star burns through the hydrogen in its core, it eventually runs out of fuel to sustain nuclear fusion. When this happens, the star's core contracts under the relentless pull of gravity, while its outer layers expand. This expansion causes the star to swell into what is known as a red giant. Our Sun, for example, will one day become a red giant, expanding to engulf the inner planets of the solar system, including Earth. For stars like the Sun, this red giant phase is followed by the shedding of their outer layers, which drift off into space to form beautiful, glowing clouds known as planetary nebulae. The core of the star, left behind, contracts into a white dwarf, a small, incredibly dense object about the size of Earth but with the mass of the Sun. Over billions of years, this white dwarf will gradually cool and fade into darkness, becoming a cold, dead remnant of its former self. Massive stars, however, meet a much more dramatic end. When a massive star exhausts the hydrogen in its core, it begins to fuse heavier elements in a series of increasingly desperate reactions. These stars can fuse elements all the way up to iron, but iron cannot undergo fusion to release energy. At this point, the core of the star collapses under its own gravity, triggering a cataclysmic explosion known as a supernova. The energy released in a supernova is so immense that, for a brief period, the star can outshine an entire galaxy. Supernovae are not just spectacular events, they are also crucial to the cosmic ecosystem. The explosion of a supernova releases heavy elements, like carbon, oxygen, and iron, into space. These elements, forged in the heart of the star, are the building blocks of planets and life. Without supernovae, the universe would be devoid of the elements necessary for the formation of complex structures like galaxies, solar systems, and living organisms. In the aftermath of a supernova, the core of the massive star can collapse into one of two exotic objects, a neutron star or a black hole. Neutron stars are incredibly dense, with masses greater than the Sun packed into a sphere only about 20 kilometers across. They are made almost entirely of neutrons, the remnants of the star's core, and are some of the most extreme objects in the universe. Neutron stars can spin at incredible speeds, sometimes hundreds of times per second, and emit beams of radiation that sweep through space like cosmic lighthouses. If the original star was massive enough, its core may collapse even further, beyond the point of no return, into a black hole. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. Once thought to be mere theoretical objects, black holes are now known to be a fundamental part of the universe, shaping the evolution of galaxies and playing a key role in the dynamics of the cosmos. Stars are also responsible for the formation of planetary systems. As a star forms from the collapse of a molecular cloud, the material around it can flatten into a rotating disk of gas and dust. Over time, this material coalesces into planets, moons, and other celestial objects, creating a solar system. Our own Sun, a relatively ordinary star, is at the center of such a system, with planets like Earth, Mars, and Jupiter orbiting around it. The relationship between a star and its planets is complex and dynamic. Stars provide the energy necessary for life, as we see on Earth, but they can also be destructive forces. Solar flares and coronal mass ejections, violent eruptions of energy and charged particles from a star's surface, can have dramatic effects on the planets in their vicinity. For planets with atmospheres and magnetic fields, like Earth, these events can cause beautiful auroras but also disrupt communication systems and power grids. For planets without such protection, solar flares can strip away the atmosphere, rendering them barren and lifeless. Stars also come in many different types, each with its own characteristics and peculiarities. In addition to the common red dwarfs, there are blue giants, white dwarfs, and variable stars, to name a few. Blue giants are some of the hottest and most massive stars in the universe, shining with a blue-white light that signifies their extremely high temperatures. These stars burn through their fuel quickly and have relatively short lifespans, often ending in spectacular supernovae. White dwarfs, as mentioned earlier, are the remnants of medium-sized stars like the Sun. These dense objects no longer undergo fusion, but they continue to shine due to the residual heat left over from their earlier stages. Over time, they will cool and fade, but this process can take billions of years. Variable stars, on the other hand, are stars whose brightness fluctuates over time. Some variable stars change brightness because they are pulsating, expanding, and contracting in a rhythmic pattern. Others vary in brightness due to interactions with a companion star, as in the case of binary star systems where two stars orbit each other closely. Binary star systems are another fascinating aspect of stellar evolution. In these systems, two stars orbit a common center of mass, bound together by gravity. Sometimes the stars are of similar mass, while in other cases one star can be much larger than the other. These systems can lead to unique phenomena, such as mass transfer between the stars, where material from one star is pulled onto the other. In some cases, this can lead to explosive events known as novae, as the transferred material ignites on the surface of the receiving star. Stars exist in clusters and groups as well, further illustrating their role as social entities within the universe. Star clusters are collections of stars that are gravitationally bound together, sharing a common origin. These clusters come in two main varieties: open clusters and globular clusters. Open clusters are groups of young stars, usually found in the spiral arms of galaxies like the Milky Way. They often contain hundreds to thousands of stars, loosely bound and scattered over relatively small regions of space. These stars were born from the same molecular cloud and are roughly the same age, though they can vary in mass. Over time, the gravitational forces of nearby stars and galaxies can cause the stars in an open cluster to drift apart, dispersing into the galaxy. Globular clusters, on the other hand, are much older and more densely packed. These spherical collections of stars can contain hundreds of thousands, even millions of stars, all tightly bound together by gravity. Globular clusters are typically found in the halos of galaxies, far from the galactic plane. The stars in globular clusters are among the oldest in the universe, with ages often exceeding 10 billion years. These ancient stars are mostly low-mass, red, and yellow stars that have long since exhausted the more volatile stages of their stellar evolution. The distribution of stars within a galaxy is another fascinating subject. Galaxies are vast collections of stars, gas, dust, and dark matter, all held together by gravity. Our galaxy, the Milky Way, is a barred spiral galaxy, with a central bulge surrounded by a disk of stars that forms the iconic spiral arms. The stars in the Milky Way are not evenly distributed. Rather, they tend to clump together in the spiral arms, which are regions of increased star formation. These arms are filled with young, hot stars, glowing brightly in the ultraviolet and blue parts of the spectrum. In contrast, the central bulge of the galaxy contains older stars, many of which are remnants of earlier stages of galactic evolution. The halo of the Milky Way, extending far beyond the visible galaxy, is home to the aforementioned globular clusters and a sparse population of older stars. The interactions between stars within a galaxy, and between galaxies themselves, drive much of the dynamism and evolution of the universe on large scales. Galaxies do not exist in isolation. They are part of even larger structures called galaxy clusters, which can contain hundreds or thousands of galaxies. The gravitational interactions between galaxies in these clusters can lead to spectacular events, such as galactic collisions. When galaxies collide, the stars within them typically do not crash into one another directly, due to the vast distances between individual stars. However, the gas and dust within the galaxies can interact, leading to intense bursts of star formation. These starburst galaxies produce new stars at an accelerated rate, often forming massive, bright, and short-lived stars. Beyond galaxy clusters, the universe itself is organized into a vast cosmic web of filaments and voids. Stars are the fundamental units of this cosmic tapestry, lighting up the universe and acting as beacons by which we can study the larger-scale structures of the cosmos. The light from distant stars and galaxies is crucial for understanding the history and evolution of the universe. As light travels across space, it carries with it information about the stars and galaxies from which it originated. By studying this light, astronomers can peer back in time, observing the universe as it was billions of years ago. One of the most important tools for studying stars is spectroscopy, the analysis of the light emitted by stars. When light passes through a prism or a diffraction grating, it is split into its component colors, or spectrum. Each element in a star's atmosphere absorbs light at specific wavelengths, creating dark lines in the star's spectrum known as absorption lines. By studying these lines, astronomers can determine the chemical composition of a star, as well as its temperature, density, and motion. Through spectroscopy, we have learned that stars are composed primarily of hydrogen and helium, the two lightest elements. These elements were created in the first few minutes after the Big Bang, during a period known as primordial nucleosynthesis. As stars form and evolve, they fuse hydrogen into helium in their cores, creating heavier elements like carbon, oxygen, and nitrogen in the process. The heaviest elements, such as gold and uranium, are created in the extreme conditions of supernovae and the mergers of neutron stars. The study of stars has revealed that the universe is not static, but is constantly changing and evolving. The discovery that galaxies are moving away from each other, as evidenced by the redshift of their light, led to the formulation of the Big Bang theory. According to this theory, the universe began as an incredibly hot and dense point about 13.8 billion years ago, and has been expanding ever since. The stars we see today are the descendants of the first stars that formed in the early universe, and their light carries the history of cosmic evolution. As we continue to study stars and the cosmos, we are confronted with profound questions about the nature of the universe and our place within it. Are there other planets orbiting distant stars that could harbor life? How do black holes and dark matter influence the formation of galaxies? What will happen to the universe in the distant future, when the last stars have burned out and the cosmos is filled with nothing but cold, dark remnants? Stars, though seemingly eternal, are transient objects on cosmic timescales. The stars we see today will not last forever, and the universe itself will undergo radical transformations over billions and trillions of years. As stars age and die, they leave behind the raw materials for new generations of stars to form. This cycle of birth, death, and rebirth is central to the ongoing evolution of the universe. Over the course of its history, the universe has gone through several epochs, each defined by different processes of star formation and destruction. In the current epoch, known as the Stelliferous Era, stars dominate the universe. This era began roughly a billion years after the Big Bang, when the first stars formed, and it is expected to continue for another 100 trillion years. During this time, galaxies will continue to evolve, and stars will continue to form from the gas and dust in interstellar space. However, as the universe expands and the available gas is used up, the rate of star formation will gradually decline. Eventually, the universe will enter a new phase, known as the Degenerate Era, when the last stars have burned out, and only the remnants of stars, white dwarfs, neutron stars, and black holes, remain. In this distant future, the universe will be a much darker and colder place, as the energy from fusion in stars will no longer be available. Over time, even these stellar remnants will decay, as white dwarfs cool to become black dwarfs, and black holes slowly evaporate through a process known as Hawking radiation. The ultimate fate of the universe is still a matter of scientific speculation, but the study of stars provides us with important clues. By understanding the life cycles of stars and their role in the larger cosmic environment, we can gain insights into the long-term future of the universe. In this sense, the study of stars is not just about understanding distant objects in the sky. It is about understanding the fundamental processes that shape our universe and our own existence within it. The discovery of exoplanets, planets orbiting stars outside our solar system, has added another dimension to our understanding of the cosmos. Since the first exoplanet was discovered in 1992, thousands of these distant worlds have been found, revealing a staggering diversity of planetary systems. Some exoplanets are similar to Earth, while others are gas giants, ice worlds, or even planets orbiting multiple stars. The study of exoplanets has opened up new possibilities in the search for life beyond our solar system, and has raised questions about the uniqueness of Earth and its place in the universe. As astronomers continue to search for exoplanets, one of the primary goals is to find Earth-like planets in the so-called habitable zone, the region around a star where conditions might be just right for liquid water to exist. This search has yielded some exciting discoveries, including several planets that are considered potential candidates for hosting life. However, it is important to note that being in the habitable zone does not guarantee that a planet is habitable. Factors like atmospheric composition, magnetic fields, and geological activity all play crucial roles in determining a planet's suitability for life. Stars themselves have a profound influence on the habitability of their planets. The type of star, its size, age, and activity all affect the conditions on surrounding planets. For example, smaller, cooler stars like red dwarfs have much longer lifespans than stars like our Sun, potentially providing a stable environment for life to develop over billions of years. However, red dwarfs are also prone to frequent and violent stellar flares, which could strip away the atmospheres of nearby planets, making them inhospitable. In contrast, larger stars, such as blue giants, burn much hotter and faster, exhausting their fuel in a few million years. While these stars may host planets, their brief lifespans make it unlikely that life, as we understand it, would have enough time to develop. The search for life in the universe is intimately tied to the study of stars, as their energy and influence create the environments in which planets and potential life forms exist. The discovery of rogue planets, planets that do not orbit any star, has further expanded our understanding of planetary systems. These wandering planets, ejected from their home systems during the chaotic processes of planet formation, drift through the galaxy in isolation. Without the light and heat of a star, rogue planets would be frozen, dark worlds, though some may have internal heat sources that could allow for the existence of subsurface oceans. The study of rogue planets challenges our assumptions about the necessity of stars for life and planetary systems. While stars are the primary source of energy for most planets, there may be other ways for life to thrive in the cosmos. For instance, life could exist in the deep oceans of rogue planets, sustained by geothermal heat rather than sunlight. Such discoveries would radically change our understanding of the potential for life in the universe. In addition to exoplanets, the study of stars has revealed the existence of exotic objects that defy our everyday understanding of physics. One of the most intriguing of these objects is the black hole, a region of space where gravity is so strong that nothing, not even light, can escape. Black holes are formed when massive stars collapse under their own gravity at the end of their life cycles. The study of black holes has revolutionized our understanding of gravity, space-time, and the nature of the universe itself. Black holes come in several varieties, ranging from stellar mass black holes, which form from the collapse of massive stars, to supermassive black holes, which are found at the centers of galaxies and can have masses millions or even billions of times that of the Sun. The formation of supermassive black holes is still a mystery, though they are thought to have formed early in the history of the universe, possibly through the mergers of smaller black holes or the direct collapse of massive gas clouds. The existence of black holes was first predicted by Albert Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by massive objects. According to this theory, a sufficiently massive object could warp space-time to such an extent that it would create a region from which nothing could escape, a black hole. While black holes were initially a theoretical construct, their existence has since been confirmed through observations of their effects on nearby stars and gas. One of the most important discoveries in recent years has been the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects, such as the collision and merger of black holes. The detection of these waves by the LIGO and Virgo observatories has opened up a new way of studying the universe, allowing us to observe events that are otherwise invisible, such as the collision of black holes and neutron stars. These observations have provided further confirmation of the existence of black holes and have given us new insights into the nature of gravity and spacetime. Stars also play a crucial role in the formation of another exotic object, the neutron star. Neutron stars are the remnants of massive stars that have undergone supernova explosions. When a star with a mass between about 8 and 25 times that of the Sun reaches the end of its life, it undergoes a catastrophic collapse, causing its core to compress into an incredibly dense object composed almost entirely of neutrons. A neutron star is so dense that a single teaspoon of its material would weigh billions of tons on Earth. Neutron stars are also incredibly hot and rotate rapidly, often emitting beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky like lighthouse beacons, and when they pass over Earth, they appear as pulses of radiation. These rapidly rotating neutron stars are known as pulsars, and they were first discovered in 1967 by astronomer Jocelyn Bell Burnell. Pulsars are among the most precise clocks in the universe, with some spinning hundreds of times per second. The discovery of pulsars has provided valuable insights into the physics of neutron stars and the extreme conditions that exist in their interiors. Neutron stars are the densest objects in the universe, other than black holes, and studying them can help us understand the behavior of matter under conditions that are impossible to replicate on Earth. The study of neutron stars also has implications for our understanding of fundamental forces, such as gravity and the strong nuclear force, which governs the behavior of particles within atomic nuclei. One of the most fascinating phenomena associated with neutron stars is the merger of two neutron stars. When two neutron stars orbit each other, they gradually lose energy through the emission of gravitational waves, causing them to spiral closer together. Eventually, they collide in a cataclysmic event known as a kilonova. These mergers are thought to be one of the primary sources of heavy elements, such as gold and platinum, in the universe. The detection of gravitational waves from a neutron star merger in 2017, along with the associated electromagnetic radiation, provided the first direct evidence of this process. Stars, in all their various forms, are not only the building blocks of galaxies and planetary systems, but also the engines of cosmic alchemy. Through the process of nuclear fusion, stars convert hydrogen into helium and, in the later stages of their life cycles, create heavier elements like carbon, oxygen, and iron. These elements are the building blocks of planets and life itself. Without the generations of stars that have lived and died over the history of the universe, the elements necessary for life would not exist. When stars reach the end of their lives, they often explode in spectacular supernovae, scattering their enriched material into space. This material is then incorporated into new stars and planets, continuing the cycle of stellar evolution. Our own solar system, including Earth, was formed from the remnants of previous generations of stars. In this sense, we are all made of star stuff, as the famous astronomer Carl Sagan once said. The study of stars has also provided us with insights into the future of our own sun and solar system. The sun is currently in the middle of its life cycle, steadily converting hydrogen into helium through nuclear fusion in its core. However, in about 5 billion years, the sun will exhaust its supply of hydrogen and begin to fuse helium into heavier elements. This will cause the sun to expand into a red giant, engulfing the inner planets, including Earth, in the process. Eventually, the sun will shed its outer layers, leaving behind a dense, hot core known as a white dwarf. The white dwarf will gradually cool and fade over billions of years, becoming a cold, dark remnant of the sun's former glory. Long before this happens, however, life on Earth will become impossible as the sun's increasing luminosity causes the planet to heat up. Understanding the life cycle of stars allows us to predict the long-term future of our solar system and the eventual fate of the sun. The study of stars is not just an intellectual pursuit, it has practical implications for life on Earth. For example, understanding the sun's behavior is critical for predicting space weather, which can have significant effects on our technology and infrastructure. Solar flares and coronal mass ejections, which are eruptions of charged particles from the sun, can cause geomagnetic storms on Earth, disrupting communication systems, power grids, and satellites. Predicting and understanding space weather has become an important field of research as our reliance on technology grows. Satellites, GPS systems, and even power grids on Earth are vulnerable to the effects of solar activity. Solar storms, which occur when the sun emits bursts of energy in the form of flares and coronal mass ejections, can send streams of charged particles toward Earth. When these particles interact with Earth's magnetic field, they can cause disturbances that affect everything from radio communications to navigation systems and power transmission. One of the most famous examples of the effects of solar storms occurred in 1859 with the Carrington event, the largest geomagnetic storm on record. The storm caused widespread disruption to telegraph systems and produced spectacular auroras that were visible as far south as the Caribbean. If a similar event were to occur today, it could cause trillions of dollars in damage to the global economy by knocking out satellites, disabling power grids, and disrupting critical communication networks. To mitigate the effects of solar storms, space agencies like NASA and the European Space Agency, ESA, monitor the sun's activity closely. Observations from solar observatories, such as the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe, allows scientists to study the sun's magnetic field and predict when solar storms are likely to occur. This information can then be used to take precautions, such as temporarily shutting down satellites or rerouting power to protect critical infrastructure. The study of stars also provides clues about the broader processes that govern the evolution of galaxies and the universe as a whole. Stars are not evenly distributed throughout the universe. They are organized into vast collections called galaxies. Our own galaxy, the Milky Way, contains hundreds of billions of stars, along with gas, dust, and dark matter, all held together by gravity. The formation and evolution of galaxies are intimately connected to the life cycles of stars, as the processes of star formation, supernovae, and black hole activity shape the structure and dynamics of galaxies. One of the key questions in modern astrophysics is how galaxies form and evolve over time. Observations of distant galaxies, combined with computer simulations, suggest that galaxies form through the gradual accumulation of gas and the mergers of smaller galaxies. In the early universe, shortly after the Big Bang, the first stars and galaxies began to form from clouds of hydrogen and helium. These early galaxies were smaller and less organized than modern galaxies, and over billions of years, they merged and grew into the massive structures we see today. The interactions between stars, gas, and dark matter play a crucial role in the evolution of galaxies. Dark matter, which makes up about 85% of the matter in the universe, exerts a gravitational pull on stars and gas, helping to hold galaxies together. Without dark matter, the gravitational forces of visible matter alone would not be sufficient to prevent galaxies from flying apart. The exact nature of dark matter remains one of the greatest mysteries in astrophysics, but its presence is inferred from the gravitational effects it has on stars and galaxies. Galactic collisions are another important process in the evolution of galaxies. When two galaxies collide, their stars do not actually collide with each other due to the vast distances between them. However, the gravitational interactions between the galaxies can cause dramatic changes in their structure. The gas within the galaxies is often compressed during the collision, triggering bursts of star formation. Over time, the two galaxies may merge to form a single, larger galaxy. Our own Milky Way is on a collision course with the nearby Andromeda Galaxy, and in about 4 billion years, the two galaxies will merge to form a new galaxy. The study of galaxy collisions has provided valuable insights into the dynamics of galaxies and the role of gravity in shaping their evolution. It has also helped us understand the role of supermassive black holes in the centers of galaxies. Most, if not all, large galaxies are thought to contain a supermassive black hole at their core. These black holes can influence the behavior of stars and gas in the galaxy, and their growth is closely linked to the overall evolution of the galaxy. As galaxies merge, their central black holes may also merge, forming an even larger black hole. The interactions between black holes and their host galaxies are complex and not yet fully understood, but observations suggest that supermassive black holes can regulate the growth of galaxies by ejecting energy and matter into their surroundings. This feedback process may help to explain why some galaxies stop forming stars and become red and dead, while others continue to form new stars for billions of years. The connection between stars and galaxies is also evident in the large-scale structure of the universe. On the largest scales, galaxies are not randomly distributed but are organized into vast cosmic webs of filaments and voids. These structures are shaped by the gravitational interactions of dark matter, galaxies, and gas, and they provide a window into the history of the universe's expansion and evolution. By studying the distribution of galaxies and the properties of stars within them, astronomers can learn about the forces that have shaped the universe since the Big Bang. One of the most remarkable discoveries in the study of stars and galaxies is the observation of the accelerating expansion of the universe. In the late 20th century, astronomers studying distant supernovae discovered that the universe is not only expanding, but that the rate of expansion is increasing over time. This discovery was a major surprise, as it was previously assumed that the expansion of the universe would slow down due to the gravitational pull of matter. The cause of this accelerated expansion is unknown, but it is attributed to a mysterious force known as dark energy, which makes up about 70% of the total energy content of the universe. Dark energy appears to have a repulsive effect, counteracting the pull of gravity and driving the expansion of the universe. The discovery of dark energy has revolutionized our understanding of the cosmos and raised profound questions about the ultimate fate of the universe. If the expansion of the universe continues to accelerate, the distant galaxies we observe today will eventually move beyond our observable horizon, disappearing from view. Over billions of years, the universe could become a cold, dark, and empty place, with only the remnants of stars and black holes remaining. This scenario, known as the Big Freeze, is one of several possible outcomes for the universe, depending on the nature of dark energy and the behavior of gravity on cosmic scales. The study of stars, from their birth to their death, provides a framework for understanding the broader processes that govern the universe. Through the light of stars, we can trace the history of the cosmos, from the formation of the first galaxies to the present day. Stars are the beacons that illuminate the vastness of space, and by studying them, we gain insight into the forces that have shaped the universe and our place within it. In addition to their scientific importance, stars have played a central role in human culture and imagination for millennia. From the earliest civilizations, people have looked up at the night sky and marveled at the stars. Ancient cultures used the positions of stars to navigate the seas, mark the passage of time. In the modern era, space exploration has allowed us to study stars up close and in ways that were once unimaginable. Space telescopes like the Hubble Space Telescope have provided stunning images of distant stars, nebulae, and galaxies, revealing the beauty and complexity of the universe. The study of stars is not just about understanding the physical processes that govern them. It is also about exploring the awe and wonder that the cosmos inspires in us. Stars are a reminder of the vastness of the universe and the smallness of our place within it. Yet, at the same time, they connect us to the larger cosmic story. We are made of the same elements that were forged in the hearts of stars billions of years ago. The light from distant stars that we see today has traveled across the universe for millions or even billions of years, carrying with it the history of the cosmos. The study of stars touches on some of the most fundamental questions of existence. Where did we come from? How did the universe come to be? What is the ultimate fate of everything? As we continue to explore and understand the stars, we uncover not only the mechanics of the universe but also our place within it. This knowledge expands our horizons and challenges us to think beyond the immediate concerns of our everyday lives. It forces us to confront the enormity of the cosmos and our smallness in comparison, while also reminding us that we are connected to the universe in profound ways. The fusion reactions in stars, which power their radiant energy, are the processes that create most of the elements that exist in the universe. Without stars, there would be no carbon, no oxygen, no nitrogen, the building blocks of life itself. Every atom in our bodies was forged in the heart of a star, making us literally stardust. This realization underscores the deep connection between humanity and the cosmos, offering a perspective that transcends the boundaries of Earth and our individual lives. Beyond their role in the creation of elements, stars also influence the conditions for life in other ways. The radiation from stars can drive the formation of planetary systems by heating the surrounding gas and dust, causing it to collapse and form planets. In turn, the energy from stars can warm these planets, potentially making them suitable for life. Our own sun is a perfect example of this. Its stable energy output has allowed life to flourish on Earth for billions of years. However, stars also pose challenges to life. Their intense radiation can strip away planetary atmospheres, and violent events such as supernovae can bathe nearby planets in deadly levels of radiation. Understanding the delicate balance between the nurturing and destructive forces of stars is crucial for determining the potential habitability of planets, both in our solar system and beyond. The search for life on other planets is closely tied to the study of stars. By studying the light from distant stars, astronomers can detect planets orbiting those stars and measure their properties. This field, known as exoplanet research, has exploded in recent years with the discovery of thousands of planets outside our solar system. Some of these planets are located in the habitable zone of their parent stars, where conditions might be right for liquid water, and potentially life, to exist. The Kepler Space Telescope, which launched in 2009, revolutionized the search for exoplanets by observing the tiny dips in a star's brightness that occur when a planet passes in front of it. These observations have revealed a staggering diversity of planetary systems, including many planets that are very different from anything we see in our solar system. From hot Jupiters, gas giants that orbit close to their stars, to rocky, Earth-sized planets in the habitable zone, the variety of planets discovered has challenged our understanding of planet formation and evolution. One of the most exciting discoveries in recent years is the detection of potentially habitable planets orbiting stars in the Milky Way. For example, the star TRAPPIST-1, located about 40 light-years from Earth, has 7 Earth-sized planets, 3 of which are in the habitable zone. The discovery of these planets has fueled hopes that life could exist elsewhere in the galaxy, and has prompted further study of the properties of stars and their planets. The James Webb Space Telescope, JWST, launched in 2021, is the next step in this search. With its powerful instruments, JWST can study the atmospheres of exoplanets in unprecedented detail, looking for signs of life, such as the presence of oxygen, methane, or other biosignature gases. By studying the light that passes through a planet's atmosphere as it transits its star, scientists can determine the chemical composition of the atmosphere and assess the planet's potential for supporting life. The discovery of life beyond Earth, if it ever happens, would be one of the most profound events in human history. It would not only confirm that we are not alone in the universe but also raise new questions about the nature of life and the conditions that allow it to arise. Studying stars and their planets is key to answering these questions, as it helps us understand the environments where life could potentially exist. Even if we never find evidence of life on other planets, the study of stars and exoplanets offers valuable insights into the diversity of planetary systems and the processes that govern their formation. It also deepens our appreciation of the uniqueness of our own solar system and the conditions that have allowed life to thrive on Earth. In addition to their scientific importance, stars have a profound influence on our cultural and philosophical perspectives. Throughout history, stars have inspired myths, legends, and stories that reflect the values and beliefs of different civilizations. The stars have been seen as symbols of eternity, guiding lights, and representations of the divine. They have been used to mark the passage of time, predict the future, and provide meaning in the face of the unknown. The philosophical implications of stars extend to questions about the nature of the universe and our place in it. The vastness of the cosmos, as revealed by the study of stars, challenges our understanding of time, space, and existence. The realization that stars are born, live, and die on timescales far beyond human experience forces us to reconsider our own significance in the grand scheme of things. For centuries, philosophers and scientists have grappled with questions about the nature of the universe and its origins. The study of stars has played a central role in shaping our understanding of these questions, from the early debates about the geocentric versus heliocentric models of the solar system to the modern exploration of cosmology and the Big Bang theory. Stars are not just points of light in the sky, they are windows into the deepest mysteries of existence. One of the most profound questions raised by the study of stars is the nature of time itself. Stars live for billions of years, far longer than any human lifespan, and their life cycles provide a glimpse into the passage of cosmic time. The light we see from distant stars has traveled for millions or even billions of years to reach us, allowing us to look back in time and see the universe as it was long before Earth existed. The concept of time on cosmic scales is difficult to comprehend, as it far exceeds the timescales we are familiar with in our everyday lives. The evolution of stars, galaxies, and the universe as a whole unfolds over timescales that dwarf human history. This realization has led to philosophical debates about the nature of time, the beginning and end of the universe, and the role of human consciousness in the grand sweep of cosmic history. In modern cosmology, the study of stars has contributed to our understanding of the Big Bang, the event that gave birth to the universe about 13.8 billion years ago. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, have provided critical evidence for the theory that the universe began as a hot, dense state and has been expanding ever since. The study of stars and galaxies has allowed astronomers to trace the history of the universe from its earliest moments to the present day. But the Big Bang theory raises new questions about the origin of the universe and what, if anything, came before it. Some cosmologists propose that the universe could be part of a larger multiverse, a collection of many universes, each with its own physical laws and conditions. Others suggest that the universe could go through cycles of expansion and contraction, with each Big Bang followed by a big crunch. These ideas challenge our understanding of time and space, as well as our assumptions about the nature of reality. As we continue to study stars and the cosmos, we are confronted with more questions than answers. The more we learn, the more we realize how much we have yet to discover. But this is the nature of science, a never-ending quest for knowledge that pushes the boundaries of our understanding and reveals new layers of complexity in the universe. Stars, in their grandeur and mystery, serve as a reminder of the vastness of the unknown. They inspire us to keep asking questions, to keep exploring, and to seek answers to the deepest mysteries of existence. Whether we are studying the birth of a new star, the death of an ancient one, or the behavior of distant galaxies, we are participating in a long tradition of inquiry that stretches back to the earliest human civilizations and will continue far into the future. In this sense, stars are not just objects of scientific study. They are symbols of our curiosity and our desire to understand the universe. They remind us of the infinite possibilities that lie beyond our world and the importance of looking up and wondering what lies out there. As we gaze at the night sky, we are not just observing distant points of light. We are glimpsing the mysteries of existence itself. The study of stars will undoubtedly continue to shape our understanding of the universe for generations to come. New discoveries, new technologies, and new ideas will push the boundaries of what we know, offering fresh insights into the workings of the cosmos. And as we continue to explore the stars, we will be reminded of our own place in the universe, small, fragile, and yet connected to the vast, unfolding story of the cosmos. As we look to the future of stellar research, there are many exciting developments on the horizon. Advanced telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, are poised to revolutionize our understanding of stars and their role in the cosmos. These next-generation observatories will be able to detect even fainter and more distant objects, revealing details that were previously hidden from us. With their unprecedented resolution and sensitivity, these instruments will allow astronomers to peer deeper into the universe than ever before. The James Webb Space Telescope, in particular, is expected to make groundbreaking discoveries in a wide range of fields, from the formation of the first stars and galaxies to the study of exoplanets and their atmospheres. One of JWST's key missions is to study the formation of stars in distant galaxies, a process that is difficult to observe because the light from these galaxies is redshifted due to the expansion of the universe. By observing in the infrared part of the spectrum, JWST will be able to detect this redshifted light and study the early stages of star formation in galaxies that are billions of light-years away. In addition to studying the formation of stars, JWST will also provide new insights into the life cycles of stars. It will be able to observe the dusty envelopes around young stars, where planets may be forming, and it will study the remnants of exploded stars, such as supernovae and neutron stars. These observations will help astronomers understand the processes that govern the birth, life, and death of stars, as well as the formation of planetary systems. The Extremely Large Telescope, ELT, currently under construction in Chile, is another highly anticipated project that will transform our understanding of stars. With a primary mirror measuring 39 meters in diameter, the ELT will be the largest optical/infrared telescope in the world. It will be able to resolve details that are 16 times finer than those seen by the Hubble Space Telescope, allowing astronomers to study individual stars in distant galaxies with unprecedented precision. One of the key goals of the ELT is to study the atmospheres of exoplanets in detail, searching for signs of life. By observing the light from stars as it passes through the atmospheres of orbiting planets, astronomers can detect the presence of gases such as oxygen, methane, and water vapor, potential indicators of life. The ELT will also study the processes that govern the formation and evolution of stars and galaxies, helping to answer fundamental questions about the structure and history of the universe. Beyond these telescopes, there are many other missions and instruments in development that will push the boundaries of our knowledge of stars. For example, the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, will detect gravitational waves from merging black holes and neutron stars, providing a new way to study these exotic objects. Meanwhile, the Square Kilometre Array, SKA, a massive radio telescope under construction in South Africa and Australia, will probe the formation of stars and galaxies by detecting the faint radio signals emitted by neutral hydrogen, the most abundant element in the universe. As we continue to develop new technologies and refine our observational techniques, our understanding of stars will become even more detailed and nuanced. We will gain deeper insights into the processes that govern their formation, evolution, and eventual demise. And with each new discovery, we will be reminded of the intricate, and dynamic nature of the universe we inhabit. One of the most fascinating aspects of stars is their ability to tell us about the history of the universe. Because light from distant stars takes time to reach us, observing these stars allows us to look back in time and see the universe as it was in the past. This is especially true for the most distant stars and galaxies, which we observe as they were billions of years ago, not long after the Big Bang. By studying these ancient stars, we can learn about the conditions that existed in the early universe and how those conditions have evolved over time. In particular, astronomers are interested in studying the first generation of stars, known as population 3 stars, which formed shortly after the Big Bang. These stars are thought to have been massive and short-lived, but their exact properties remain a mystery because none have yet been observed. Detecting these primordial stars would provide critical insights into the formation of the first galaxies and the processes that led to the creation of the elements that make up everything we see today. As we look farther and farther back in time, we also gain a better understanding of how galaxies have evolved. Galaxies are the homes of stars, and their formation and evolution are closely tied to the life cycles of stars. By studying the stars and different types of galaxies, astronomers can piece together the history of galaxy formation and the role that stars have played in shaping the structure of the universe. Another exciting area of research is the study of the interstellar medium, the gas and dust that exists between the stars and galaxies. This material plays a crucial role in the formation of new stars, as it provides the raw ingredients for star formation. When stars die, they return some of their material to the interstellar medium, enriching it with heavy elements that were forged in their cores. This recycled material can then form new generations of stars, continuing the cycle of stellar evolution. Studying the interstellar medium helps astronomers understand the processes that regulate star formation in galaxies, as well as the feedback mechanisms that can either promote or suppress star formation. For example, supernovae, the explosive deaths of massive stars, can inject enormous amounts of energy into the surrounding gas, heating it up and preventing new stars from forming. On the other hand, the shock waves from supernovae can also compress the gas and trigger the formation of new stars. The interplay between stars and the interstellar medium is a key factor in determining the rate of star formation in galaxies. Some galaxies, such as the Milky Way, are still actively forming stars, while others, known as quenched galaxies, have little or no star formation. Understanding why some galaxies continue to form stars while others do not is one of the major questions in modern astrophysics. In addition to studying the interstellar medium, astronomers are also interested in the environments around stars, particularly the regions where planets form. These regions, known as protoplanetary disks, are made up of gas and dust that orbit young stars. Over time, the material in these disks can coalesce to form planets, moons, asteroids, and other objects. By observing protoplanetary disks, astronomers can study the early stages of planet formation and learn about the conditions that give rise to planetary systems. In recent years, observations with the Atacama Large Millimeter/Submillimeter Array, ALMA, and other telescopes have revealed detailed images of these disks, showing structures such as rings, gaps, and spiral arms that are thought to be caused by the presence of forming planets. These observations are helping to answer fundamental questions about how planets form and evolve, and they are providing important clues about the diversity of planetary systems in the universe. For example, many of the planets discovered in other solar systems are very different from those in our own solar system, with some being much larger or smaller, or orbiting their stars at much closer distances. Studying protoplanetary disks can help explain how such a wide variety of planetary systems arises. As we continue to study stars and their planets, we are also gaining new insights into the conditions that make planets habitable. One of the key factors is the star itself. The amount of energy a star emits, as well as its stability over time, plays a crucial role in determining whether a planet can support life. For example, stars that emit too much ultraviolet radiation can strip away a planet's atmosphere, while stars that are too dim may not provide enough energy for life to exist. The search for habitable planets is closely tied to the study of stars. By understanding the properties of different types of stars, we can better assess the likelihood of finding planets that could support life. For example, scientists have identified a habitable zone around stars, where conditions might be right for liquid water to exist on the surface of a planet. This zone is determined by the distance from the star and the star's energy output. Studying stars of different types, from cool red dwarfs to hot blue giants, helps astronomers refine their models of habitability and search for potentially life-bearing planets. One of the most exciting discoveries in recent years has been the detection of exoplanets, planets orbiting stars outside our solar system. Since the first confirmed detection of an exoplanet in the 1990s, astronomers have identified thousands of these distant worlds, and the list continues to grow with every new observation. This discovery has not only expanded our understanding of the universe but also raised profound questions about the possibility of life elsewhere. The study of exoplanets has fundamentally changed how we view stars, as planets are now understood to be common around them. Most of the stars in the universe are likely to have planetary systems, with many hosting multiple planets. As a result, the search for exoplanets has become a major focus of modern astronomy. These discoveries are primarily driven by missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, which search for planets by detecting the tiny dips in starlight that occur when a planet passes in front of its host star, a method known as the transit method. Exoplanet discoveries have revealed a staggering diversity of planetary systems. Some planets are much larger than Jupiter, while others are smaller than Earth. There are planets with extremely short orbital periods, completing a full revolution around their stars in just a few days, and others with highly eccentric orbits. Some exoplanets orbit two stars, like Tatooine in Star Wars, and others may be rogue planets, drifting through space without a star at all. Among the most intriguing exoplanets are those that reside in the so-called habitable zone of their stars. This is the region where conditions might be right for liquid water to exist on the planet's surface, a key ingredient for life as we know it. Several Earth-sized planets have been discovered in these habitable zones, sparking hopes that they could harbor life. However, many factors beyond just being in the habitable zone affect a planet's potential to support life, such as the planet's atmosphere, composition, and the stability of its star. Red dwarf stars, the most common type of star in the universe, are of particular interest in the search for habitable exoplanets. These stars are much cooler and dimmer than the Sun, so their habitable zones are much closer to the star. As a result, planets in the habitable zones of red dwarfs are more likely to be tidally locked, meaning one side of the planet always faces the star while the other side remains in darkness. This could create extreme temperature differences between the two sides of the planet, posing challenges for habitability. However, it is possible that atmospheric circulation could moderate these temperature extremes, making these planets more hospitable. In addition to the transit method, astronomers use other techniques to detect exoplanets. One of the most successful methods is radial velocity, which measures the tiny wobble of a star caused by the gravitational pull of an orbiting planet. This technique has been particularly effective in discovering massive planets, known as hot Jupiters, which orbit very close to their stars. These gas giants are thought to have migrated inward from where they originally formed, a process that has significant implications for the formation of planetary systems. Direct imaging is another method used to detect exoplanets, though it is much more challenging because the light from the planet is often overwhelmed by the light from the host star. However, recent advances in technology have made it possible to directly image a small number of exoplanets, providing valuable information about their atmospheres and compositions. This technique has the potential to reveal even more about the diversity of planetary systems and the conditions on distant worlds. The study of exoplanets is still in its infancy, but it has already transformed our understanding of the universe. As new telescopes come online, such as the James Webb Space Telescope, astronomers will be able to study the atmospheres of exoplanets in greater detail, searching for signs of water, methane, carbon dioxide, and other molecules that could indicate the presence of life. This will mark a significant step forward in our quest to answer one of humanity's oldest questions: are we alone in the universe? While exoplanets are a relatively new area of study, they are deeply connected to our understanding of stars. Stars are the engines of planetary systems, providing the energy that drives planetary climates and the conditions that allow life to exist. By studying stars, we can learn more about the environments in which planets form and evolve. For example, the activity of a star, such as solar flares and stellar winds, can have a significant impact on the atmospheres of orbiting planets. In some cases, strong stellar winds or flares could strip away a planet's atmosphere entirely, making it uninhabitable. The relationship between stars and their planets is a complex one, and understanding it requires a deep knowledge of both stellar and planetary science. For instance, the presence of a large gas giant like Jupiter in a planetary system can help protect smaller, rocky planets like Earth from frequent impacts by comets and asteroids, a phenomenon known as gravitational shielding. This protective role of gas giants may have been crucial for the development of life on Earth. In addition to their role in planetary systems, stars have a profound influence on the larger structure of the universe. Stars are the primary sources of light and energy in the cosmos, and their distribution and properties shape the appearance and dynamics of galaxies. In fact, galaxies are often classified based on the types of stars they contain. For example, spiral galaxies like the Milky Way are home to young, hot, blue stars, while elliptical galaxies are dominated by older, cooler, red stars. The color and temperature of stars provide important clues about their age and chemical composition. Blue stars are typically young and massive, burning their fuel at a much faster rate than smaller, cooler red stars. These blue stars often form in regions of galaxies where new star formation is occurring, known as star-forming regions or stellar nurseries. In contrast, red stars tend to be older and less massive, representing the end stages of stellar evolution. The distribution of stars in galaxies also reveals much about the dynamics of these vast systems. In spiral galaxies, stars are concentrated in the spiral arms, which are regions of active star formation. These arms are created by density waves that compress gas and dust, triggering the formation of new stars. The central bulge of a spiral galaxy, on the other hand, is typically populated by older stars, while the outer regions, known as the halo, contain scattered populations of old, metal-poor stars and globular clusters. Elliptical galaxies, in contrast, contain little or no ongoing star formation. These galaxies are thought to be the remnants of major mergers between smaller galaxies, and they are dominated by older stars. Because elliptical galaxies lack the dense gas and dust required for new star formation, they are much less active than spiral galaxies. Instead, their stellar populations gradually evolve over time, with the brightest stars eventually burning out and leaving behind stellar remnants such as white dwarfs, neutron stars, and black holes. The study of stars and galaxies is not only important for understanding the structure and evolution of galaxies themselves, but it also provides key insights into the history of the universe. By observing the light from distant galaxies, astronomers can trace the history of star formation over cosmic time, revealing how galaxies grew and evolved. One of the key discoveries in this area has been the realization that the rate of star formation in the universe has declined dramatically over the past few billion years. This decline is thought to be linked to the depletion of the cold gas reservoirs that fuel star formation, as well as the feedback from supermassive black holes at the centers of galaxies, which can heat up the gas and prevent new stars from forming. In addition to their role in galaxies, stars are also important for understanding the large-scale structure of the universe. The light from stars is used to map the distribution of galaxies across the cosmos, revealing the intricate web-like structure of the universe, known as the cosmic web. This structure is shaped by the gravitational pull of dark matter, a mysterious substance that makes up about 85% of the mass in the universe. By studying the distribution of stars and galaxies, astronomers can infer the presence of dark matter and gain insights into the underlying structure of the universe. Stars also play a crucial role in the process of cosmic reionization, a key event in the history of the universe. After the Big Bang, the universe was filled with a hot, dense plasma of protons and electrons. As the universe expanded and cooled, these particles combined to form neutral hydrogen, plunging the universe into a period known as the Cosmic Dark Ages. It wasn't until the first stars and galaxies began to form, several hundred million years later, that the universe was reionized, the process by which ultraviolet light from the first stars and galaxies stripped electrons from hydrogen atoms, making the universe transparent to light once again. The study of cosmic reionization is an active area of research, as it holds important clues about the formation of the first stars and galaxies. By studying the light from distant quasars, which are powered by supermassive black holes at the centers of galaxies, astronomers can probe the state of the intergalactic medium during the epoch of reionization and learn about the conditions that allowed the first stars to form. The formation of the first stars during the cosmic reionization era was a monumental event, as these stars were significantly different from the stars we see today. The earliest stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, the lightest elements formed in the Big Bang. These stars were massive, hot, and short-lived, often exploding as supernovae within a few million years of their formation. Population 3 stars played a crucial role in enriching the universe with heavier elements, or metals, through their supernova explosions. These metals were incorporated into the next generations of stars, leading to the formation of population 2 and population 1 stars, which contain increasing amounts of heavy elements. Understanding the properties and evolution of population 3 stars is essential for reconstructing the early history of the universe, but detecting these stars directly is extremely difficult. They are too faint and too distant to be observed with current telescopes, and their short lifespans mean that they no longer exist in the present-day universe. However, astronomers hope that future telescopes, such as the James Webb Space Telescope, will be able to detect the light from these early stars by looking at extremely distant galaxies, effectively peering back in time to the early universe. The discovery of the first stars and galaxies also marked the end of the cosmic dark ages and the beginning of the cosmic dawn. During this period, the universe transitioned from a cold, dark place to one filled with light and structure. As more and more stars formed, they grouped together into galaxies, and galaxies grouped into clusters, eventually creating the large-scale structure of the universe that we observe today. The process of galaxy formation is driven by the gravitational pull of dark matter, which provides the scaffolding around which galaxies form and grow. Stars within galaxies continue to evolve over billions of years, shaping the galaxies themselves. Massive stars live fast and die young, exploding as supernovae and enriching the interstellar medium with heavy elements. These elements are then incorporated into new stars, planets, and other celestial objects. In contrast, smaller stars like the Sun have much longer lifespans, slowly fusing hydrogen into helium over billions of years. When they exhaust their nuclear fuel, they shed their outer layers and leave behind a white dwarf, a dense, slowly cooling remnant. The life cycles of stars are critical to the chemical evolution of galaxies. The process of nucleosynthesis, which occurs within the cores of stars, creates the elements that make up everything we see around us, from the oxygen we breathe to the iron in our blood. In this way, stars are not only the engines of light and energy in the universe, but they are also the forges of the elements that make life possible. As stars evolve and die, they leave behind a variety of stellar remnants. White dwarfs are the end state of stars like the Sun, but more massive stars can end their lives in more dramatic ways. Stars that are between about 8 and 20 times the mass of the Sun can end as neutron stars, incredibly dense objects composed almost entirely of neutrons. These stars are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars also possess incredibly strong magnetic fields, and some of them emit beams of radiation as they spin, becoming pulsars, one of the most precise clocks in the universe. Stars more than 20 times the mass of the Sun can collapse into black holes when they die. Black holes are objects so dense that not even light can escape their gravitational pull, making them invisible to direct observation. However, astronomers can detect black holes by observing their effects on nearby objects. For example, if a black hole is part of a binary star system, it can pull material from its companion star, creating an accretion disk of hot, glowing gas that emits X-rays. This process allows astronomers to infer the presence of a black hole even though the black hole itself cannot be seen. Supermassive black holes, which are millions to billions of times the mass of the Sun, are found at the centers of most galaxies, including our own Milky Way. These enormous black holes are thought to have formed early in the universe, perhaps from the collapse of massive clouds of gas or the merging of smaller black holes. They play a key role in the evolution of galaxies, regulating star formation through the release of energy as they accrete matter. This energy can heat up the gas in a galaxy, preventing it from cooling and forming new stars. In this way, supermassive black holes act as a feedback mechanism, controlling the growth and evolution of galaxies. The interaction between stars and black holes is a fascinating area of study, particularly in the context of gravitational waves. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as two merging black holes or neutron stars. These waves were first predicted by Albert Einstein's theory of general relativity, but they were only detected for the first time in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, experiment. The detection of gravitational waves has opened up a new window into the universe, allowing astronomers to study events that would otherwise be invisible, such as the mergers of black holes and neutron stars. The study of gravitational waves is still in its early stages, but it promises to revolutionize our understanding of stars, black holes, and the universe as a whole. By detecting the mergers of massive objects, astronomers can learn more about the population of black holes and neutron stars in the universe, as well as the conditions under which these mergers occur. In addition, gravitational waves provide a unique test of general relativity, allowing scientists to probe the nature of gravity in extreme environments. Stars also play a central role in one of the most mysterious phenomena in the universe, dark matter. While dark matter does not emit, absorb, or reflect light, its presence can be inferred through its gravitational effects on visible matter, such as stars and galaxies. In fact, stars were crucial in the discovery of dark matter, as astronomers noticed that the outer regions of galaxies were rotating much faster than expected based on the amount of visible matter they contained. This led to the realization that most of the mass in galaxies, and in the universe, is made up of dark matter. Dark matter is thought to make up about 85% of the mass in the universe, but its nature remains unknown. One leading theory is that dark matter consists of particles that interact only through gravity and possibly the weak nuclear force, making them difficult to detect. Various experiments are underway to try to detect dark matter particles directly, but so far, none have been successful. In the meantime, astronomers continue to study the effects of dark matter on galaxies and clusters of galaxies, using the motion of stars to map the distribution of dark matter in the universe. While dark matter is an essential component of the universe, stars also play a role in another mysterious phenomenon, dark energy. Unlike dark matter, which is thought to have a gravitational pull, dark energy is a form of energy that is causing the expansion of the universe to accelerate. This discovery, made in the late 1990s through observations of distant supernovae, has upended our understanding of the cosmos. The exact nature of dark energy is unknown, but it is thought to make up about 70% of the total energy density of the universe. The discovery of dark energy has profound implications for the ultimate fate of the universe. If the expansion of the universe continues to accelerate, the universe could eventually enter a phase known as the Big Freeze, where galaxies become so far apart that they are no longer visible to each other, and the stars within galaxies slowly burn out. Alternatively, if dark energy behaves in certain ways, it could lead to a Big Rip, where the acceleration becomes so extreme that galaxies, stars, planets, and even atoms are torn apart. These scenarios are still speculative, and much more research is needed to understand the true nature of dark energy and its impact on the future of the universe. Stars, therefore, are not just individual objects of study but are deeply intertwined with some of the most fundamental mysteries of the universe. From their formation and evolution to their role in galaxy dynamics and cosmology, stars offer a window into the workings of the cosmos. The light from distant stars allows us to peer back in time, to the earliest moments of the universe, while the study of nearby stars provides insights into the future of our own solar system. As we continue to explore the universe, stars will remain at the heart of our quest for knowledge. They are the building blocks of galaxies, the creators of elements, and the beacons of light that guide our exploration of the cosmos. The study of stars is not just a scientific endeavor, it is a journey of discovery that connects us to the larger universe and our place within it. As telescopes became more advanced, astronomers were able to observe stars in greater detail and begin to classify them based on their properties. In the late 19th and early 20th centuries, astronomers such as Annie Jump Cannon and Henrietta Swan Leavitt made important contributions to the classification of stars based on their spectral types and luminosities. Cannon's work on the Harvard Spectral Classification System, which organizes stars by their temperatures and spectral lines, remains a cornerstone of stellar astronomy today. Henrietta Swan Leavitt's discovery of the relationship between the luminosity and period of Cepheid variable stars was another breakthrough. Cepheid variables are a type of star that pulsates in brightness over a regular period, and Leavitt found that the longer the period of pulsation, the more luminous the star. This discovery provided astronomers with a powerful tool for measuring distances to faraway galaxies, as they could use Cepheid variables as standard candles to determine how far away the galaxies were based on the star's brightness and pulsation periods. Leavitt's work laid the foundation for Edwin Hubble's discovery in the 1920s that the universe is expanding. Hubble used Cepheid variable stars to measure the distances to galaxies, and he found that more distant galaxies were moving away from us at faster speeds. This observation led to the formulation of Hubble's law, which describes the relationship between the distance to a galaxy and its recessional velocity. Hubble's discovery of the expanding universe provided strong evidence for the Big Bang theory, which posits that the universe began as a hot, dense point about 13.8 billion years ago and has been expanding ever since. The study of stars has also advanced our understanding of the fundamental forces of nature, particularly nuclear fusion. In the early 20th century, scientists such as Arthur Eddington and Hans Bethe developed models of stellar structure and energy generation, showing that stars shine by converting hydrogen into helium through nuclear fusion. This process releases enormous amounts of energy, which counteracts the gravitational collapse of the star and allows it to maintain its stability over millions to billions of years. Nuclear fusion is the key to understanding the life cycles of stars. As stars age, they go through various stages of fusion, burning different elements in their cores as they exhaust their supply of hydrogen. Low-mass stars like the Sun eventually run out of hydrogen and helium and become white dwarfs, while more massive stars can continue fusing heavier elements until they reach iron, at which point fusion can no longer generate energy. The core of the star then collapses, leading to a supernova explosion, which can either leave behind a neutron star or a black hole, depending on the mass of the original star. The process of nuclear fusion in stars not only generates energy but also creates the elements that make up the universe. The fusion of hydrogen and helium in the cores of stars produces the lighter elements, while heavier elements such as carbon, oxygen, and iron are produced in more massive stars or during supernova explosions. This process of stellar nucleosynthesis is responsible for the creation of most of the elements found on Earth, including the elements that make up living organisms. In a very real sense, the atoms that make up our bodies were forged in the hearts of stars, a fact that underscores the deep connection between stars and life on Earth. Stars also play a critical role in the search for extraterrestrial life. One of the key factors in the search for habitable planets is the type of star around which a planet orbits. Stars that are too hot or too cold may not provide the right conditions for liquid water to exist on a planet's surface, which is considered a key requirement for life as we know it. In addition, the stability and longevity of a star are important factors in determining whether life has had enough time to develop on a nearby planet. Stars that are too massive burn through their fuel quickly and may not provide the stable environment needed for life to evolve. The search for exoplanets, planets outside our solar system, has been one of the most exciting areas of astronomy in recent years. Since the first discovery of an exoplanet in 1992, thousands of planets have been detected around other stars, many of them in the so-called habitable zone, where conditions might be right for liquid water to exist. These discoveries have been made possible by missions such as NASA's Kepler Space Telescope, which used the transit method to detect the slight dimming of a star's light as a planet passed in front of it. By studying the light from distant stars, astronomers can infer the presence of planets and learn about their properties, such as their size, composition, and atmosphere. The discovery of exoplanets has profound implications for our understanding of the universe and our place in it. It suggests that planets are common around stars and that many of these planets may be capable of supporting life. While no definitive evidence of extraterrestrial life has been found, the search for habitable planets and the study of stars continue to fuel our curiosity about the potential for life beyond Earth. In addition to the search for exoplanets, astronomers are also studying the environments around stars to better understand the processes that shape planetary systems. The protoplanetary disks of gas and dust that surround young stars are the birthplaces of planets, and by studying these disks, scientists can learn how planets form and evolve. Observations of these disks with telescopes such as the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided stunning images of planets forming within these disks, offering direct evidence of the process of planetary formation. Stars, then, are not only the creators of the elements, but also the cradles of planetary systems. They are the engines of the cosmos, driving the formation of galaxies, the evolution of planetary systems, and the conditions necessary for life. The study of stars has revealed the interconnectedness of the universe, showing that the same physical processes that govern the behavior of stars also shape the formation of planets and the conditions for life. Stars, as the engines of the cosmos, continue to be at the heart of many of the most profound questions in astronomy and cosmology. One of the most fascinating areas of study in recent decades has been the examination of stars at different stages of their life cycles. These life cycles can reveal a great deal about the evolution of galaxies, the creation of elements, and the ultimate fate of the universe. The life cycle of a star begins when a region of a molecular cloud, also known as a stellar nursery, collapses under the force of its own gravity. As the cloud contracts, it begins to heat up, eventually forming a protostar. This early stage of star formation is often shrouded in dense clouds of gas and dust, making it difficult to observe directly. However, advancements in infrared astronomy have allowed scientists to peer through these clouds and study the formation of stars in greater detail. As the protostar continues to collapse and heat up, it eventually reaches a temperature where nuclear fusion can begin in its core. At this point, the star enters the main sequence phase, where it will spend the majority of its life. During this phase, hydrogen atoms in the core of the star are fused together to form helium, releasing a tremendous amount of energy in the process. This energy is what powers the star and causes it to shine. The length of time a star spends on the main sequence depends on its mass. More massive stars burn through their hydrogen fuel much more quickly than smaller stars. For stars like our Sun, the main sequence phase lasts for billions of years. However, the story of a star's life does not end once it exhausts its hydrogen fuel. Once the hydrogen in the core is depleted, the star begins to evolve into a new phase. For low to medium mass stars, like the Sun, this evolution leads to the red giant phase. During this stage, the core contracts and heats up, causing the outer layers of the star to expand and cool. The star becomes much larger and redder, and its luminosity increases significantly. In the core of a red giant, helium fusion begins, producing carbon and oxygen. Once the helium is exhausted, the star sheds its outer layers, creating a beautiful structure known as a planetary nebula. What remains is the hot core of the star, which cools and contracts to form a white dwarf. White dwarfs are incredibly dense objects, typically about the size of Earth but with a mass similar to that of the Sun. Over billions of years, a white dwarf will slowly cool and fade, eventually becoming a cold, dark remnant known as a black dwarf, although the universe is not yet old enough for any black dwarfs to exist. For more massive stars, the story is even more dramatic. When a star more than 8 times the mass of the Sun exhausts its hydrogen fuel, it undergoes a series of nuclear fusion reactions that produce progressively heavier elements, from helium to carbon, oxygen, neon, and silicon, all the way up to iron. However, iron is the most stable element, and fusion beyond iron does not produce energy. Once a massive star builds up an iron core, it can no longer support itself against the force of gravity. The core collapses in a fraction of a second, and the outer layers of the star are blown off in a titanic explosion known as a supernova. Supernovae are among the most powerful events in the universe, releasing more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. These explosions are also responsible for creating many of the heavy elements in the universe, such as gold, uranium, and lead, which are dispersed into space and incorporated into new stars, planets, and even living organisms. After a supernova, the fate of the remaining core depends on the mass of the original star. If the core is between about 1.4 and 3 times the mass of the Sun, it will collapse into a neutron star. Neutron stars are incredibly dense objects, with a mass greater than the Sun packed into a sphere only about 20 kilometers across. The matter in a neutron star is so dense that a single teaspoonful would weigh billions of tons. Neutron stars also have extremely strong magnetic fields and can rotate rapidly, emitting beams of radiation from their poles. If these beams sweep past Earth, we observe the neutron star as a pulsar, a type of rapidly spinning neutron star that emits regular pulses of radiation. If the core of the star is more than about 3 times the mass of the Sun, it will collapse into a black hole. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole, beyond which nothing can escape, is called the event horizon. Inside the event horizon, the gravitational pull is so strong that the laws of physics as we understand them break down, and the core of the black hole collapses to a point of infinite density, known as a singularity. The formation of black holes is one of the most mysterious and fascinating aspects of stellar evolution. While black holes themselves cannot be observed directly, their presence can be inferred through their gravitational effects on nearby objects. For example, if a black hole is part of a binary system, it can pull matter from its companion star, creating a disk of superheated gas that emits X-rays. Astronomers have also detected gravitational waves, ripples in spacetime, produced by the collision and merger of black holes, providing further evidence of their existence. The study of black holes has led to some of the most intriguing questions in modern physics, particularly in the field of quantum mechanics and general relativity. The fact that black holes have a singularity, where the curvature of spacetime becomes infinite, suggests that our current understanding of physics is incomplete. Resolving the paradoxes associated with black holes, such as the information paradox, is one of the key challenges in the search for a theory of quantum gravity. Beyond their role in stellar evolution, black holes may also play a crucial role in the evolution of galaxies. Supermassive black holes, with masses millions to billions of times that of the Sun, are found at the centers of most galaxies, including our own Milky Way. These black holes are thought to have formed in the early stages of galaxy formation and may have influenced the growth and structure of galaxies by regulating the flow of gas and stars. The discovery of quasars, which are powered by supermassive black holes accreting matter at extremely high rates, has provided further evidence of the connection between black holes and galaxy evolution. Quasars are some of the most luminous objects in the universe, outshining entire galaxies. They are powered by the accretion of matter onto supermassive black holes, which heats the surrounding gas to millions of degrees and causes it to emit enormous amounts of radiation. The study of quasars has allowed astronomers to probe the early universe, as the light from distant quasars takes billions of years to reach us, providing a glimpse of what the universe was like when it was only a fraction of its current age. The connection between black holes, quasars, and galaxy evolution highlights the intricate and dynamic nature of the universe, where the life cycles of stars and the formation of galaxies are interconnected in ways that we are only beginning to understand. The study of stars, from their formation in stellar nurseries to their deaths in supernovae and black holes, provides a window into the processes that have shaped the cosmos over billions of years. In addition to their role in galaxy evolution, stars also provide a key to understanding one of the most profound mysteries in cosmology: the ultimate fate of the universe. The expansion of the universe, first discovered by Edwin Hubble, is driven by a mysterious force known as dark energy, which makes up about 70% of the total energy content of the universe. The nature of dark energy is still unknown, but its effects are observable in the accelerating expansion of the universe. If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate, leading to what is known as the Big Freeze. In this scenario, galaxies will drift apart, stars will burn out, and the universe will become a cold, dark, and empty place. Alternatively, if the nature of dark energy changes or if some other force counteracts its effects, the universe could undergo a big crunch, where the expansion slows and reverses, causing the universe to collapse back in on itself. The life cycles of stars, from their formation to their deaths, offer a glimpse into the broader processes that govern the fate of the universe. As stars burn through their fuel and die, they contribute to the creation of new stars and planets, continuing the cycle of cosmic evolution. The elements forged in the hearts of stars are the building blocks of everything we see around us, from the planets in our solar system to the atoms in our own bodies. Stars are not only key players in the cosmic cycle of creation and destruction, but they also act as cosmic laboratories where the fundamental forces of nature, gravity, electromagnetism, and nuclear forces, come together in a delicate balance. Through the fusion processes that occur in the hearts of stars, the universe is constantly being enriched with heavier elements. Without this stellar alchemy, there would be no complex chemistry, no planets, and no life as we know it. Stars are responsible for synthesizing virtually all the elements in the periodic table, with the exception of the very lightest elements, hydrogen, helium, and traces of lithium, which were formed during the Big Bang. The heavier elements, such as carbon, oxygen, and iron, are created through nuclear fusion inside stars. This process begins with hydrogen atoms fusing to form helium, releasing energy that powers the star. As the star ages and exhausts its hydrogen supply, it begins fusing heavier elements in its core, building up progressively more complex nuclei. For stars that are more massive than the Sun, this fusion process can create elements all the way up to iron. However, the creation of elements heavier than iron requires an enormous input of energy, which is provided during the explosive deaths of stars in supernovae. During a supernova, the intense heat and pressure cause protons and neutrons to combine into heavier elements, such as gold, platinum, and uranium. These newly formed elements are then scattered into space, where they can be incorporated into new stars, planets, and even living organisms. In fact, every atom in our bodies heavier than hydrogen was forged in the heart of a star. The carbon in our cells, the calcium in our bones, and the iron in our blood were all created through stellar fusion and spread across the galaxy by supernova explosions. This cosmic connection between stars and life has led to the poetic idea that we are all made of star stuff, a phrase popularized by the astronomer Carl Sagan. It's a humbling thought that the atoms that make up our bodies were once part of distant stars that lived and died billions of years ago. Stars, therefore, not only illuminate the night sky but also play a direct role in the evolution of life. Without stars, there would be no planets for life to emerge on, no heat or light to sustain it, and no elements to build the complex molecules necessary for life. This realization has fueled the search for planets around other stars, in the hope of finding other worlds where life might exist. The discovery of exoplanets, planets orbiting stars outside our solar system, has revolutionized our understanding of the universe. For much of human history, we had no way of knowing whether other planets existed, let alone whether they could support life. However, with the development of advanced telescopes and detection methods, astronomers have now identified thousands of exoplanets, many of which lie in the so-called habitable zone, around their parent stars, where conditions might be right for liquid water to exist. One of the most important tools in the search for exoplanets has been the Kepler Space Telescope, which was launched in 2009 and has discovered thousands of planets by detecting the tiny dimming of a star's light as a planet passes in front of it. This method, known as the transit method, has allowed astronomers to identify a wide variety of planets, from gas giants like Jupiter to rocky planets similar in size and composition to Earth. Some of the most exciting discoveries have been of exoplanets that are located in the habitable zones of their stars, where conditions might be suitable for life. These planets, often referred to as Earth-like planets, have fueled speculation about the possibility of finding extraterrestrial life. While we have yet to find definitive evidence of life on another planet, the discovery of so many potentially habitable worlds has made it seem more plausible than ever that life might exist elsewhere in the universe. The study of exoplanets has also shed light on the diversity of planetary systems in the universe. Our solar system, with its small rocky planets close to the Sun and its gas giants farther out, may not be typical. Many of the exoplanets discovered so far are super-Earths, planets larger than Earth but smaller than Neptune, that occupy a middle ground between the rocky and gas giant worlds in our solar system. There are also many hot Jupiters, gas giants that orbit very close to their stars, much closer than any planet in our solar system orbits the Sun. This diversity of planetary systems has raised new questions about how planets form and evolve. The discovery of hot Jupiters, for example, has challenged traditional models of planet formation, which suggests that gas giants should form far from their stars, where temperatures are cool enough for volatile compounds to condense into ices. The fact that we see gas giants so close to their stars suggests that planetary migration, where planets move inward or outward from their initial orbits, may be a common occurrence in the universe. The discovery of exoplanets has also highlighted the importance of stars in determining the habitability of planets. The type of star a planet orbits plays a crucial role in shaping the planet's environment. For example, stars that are much more massive than the Sun burn through their fuel quickly and emit large amounts of ultraviolet radiation, which could strip away the atmospheres of nearby planets and make it difficult for life to emerge. On the other hand, stars that are much smaller and cooler than the Sun, such as red dwarfs, have much longer lifespans and are more likely to host habitable planets, although they can also emit dangerous flares that might pose a threat to life. One of the most intriguing aspects of the search for exoplanets is the possibility of finding planets around binary star systems, systems where two stars orbit each other. While it was once thought that planets in such systems would be unlikely to form or survive due to the gravitational influence of two stars, recent discoveries have shown that planets can indeed exist in binary systems. These circumbinary planets, which orbit both stars, offer a fascinating glimpse into the complexity of planetary dynamics. Stars, therefore, not only provide the light and energy necessary for life, but they also shape the environments of the planets that orbit them. The study of stars and exoplanets has revealed that the universe is far more diverse and dynamic than we ever imagined, with countless worlds waiting to be explored. As we continue to study stars and their planets, we are also gaining new insights into the origins of our own solar system. By studying the composition of other stars and the planets that orbit them, we can learn more about the conditions that existed when our solar system formed. For example, the discovery of stars with higher levels of certain elements, such as oxygen and silicon, suggests that these stars may be more likely to host rocky planets like Earth. The study of stars has also helped us understand the history of our galaxy, the Milky Way. By measuring the ages of stars and the distribution of elements in the galaxy, astronomers have been able to piece together a rough timeline of how the Milky Way formed and evolved. Our galaxy, like many others, is thought to have formed through the merging of smaller galaxies, and the study of stars has provided key evidence to support this idea. One of the most exciting recent developments in the study of stars has been the discovery of gravitational waves, ripples in space-time caused by the acceleration of massive objects, such as merging black holes or neutron stars. The detection of gravitational waves has opened up a new way of studying the universe, allowing astronomers to observe events that would otherwise be invisible. In 2017, the first detection of gravitational waves from the merger of two neutron stars provided a wealth of new information about these exotic objects, including the fact that such mergers can create heavy elements like gold and platinum. Gravitational wave astronomy is still in its infancy, but it promises to revolutionize our understanding of the universe in much the same way that the discovery of exoplanets did. By detecting the ripples in space-time caused by the most violent events in the universe, astronomers can study the properties of black holes, neutron stars, and other extreme objects in unprecedented detail. As we continue to study stars, we are not only learning more about the universe, but we are also gaining new insights into our place in it. Stars are the engines of cosmic evolution, creating the elements that make life possible and illuminating the dark reaches of space. Their light has guided humanity for millennia, and their study continues to inspire new discoveries and deepen our understanding of the cosmos. Stars are remarkable because they are not merely points of light in the night sky but dynamic and evolving entities. Their life cycles, from birth to death, are some of the most spectacular events in the universe, spanning millions to billions of years depending on the mass of the star. To understand the life cycle of a star, we begin at the moment of its formation, deep within vast clouds of gas and dust known as nebulae. Nebulae are the stellar nurseries of the universe, places where new stars are born. These clouds are made primarily of hydrogen, the most abundant element in the universe, with small amounts of helium and trace elements. Gravity plays the leading role in star formation. When a region within a nebula begins to collapse under its own gravity, the material in the cloud starts to clump together. As the cloud collapses, it begins to spin, forming a rotating disk of gas and dust with a dense core at the center. This core, known as a protostar, continues to gather mass from the surrounding cloud, and as it does, the pressure and temperature at its center increase dramatically. Once the core becomes hot enough, around 10 million degrees Celsius, nuclear fusion ignites. In this process, hydrogen atoms are fused together to form helium, releasing an enormous amount of energy in the form of light and heat. At this point, the protostar has become a main sequence star, the longest and most stable phase of a star's life. Main sequence stars, like our Sun, spend most of their lives fusing hydrogen into helium in their cores. The energy produced by this fusion creates an outward pressure that balances the inward pull of gravity, keeping the star stable. For stars like the Sun, this phase lasts for billions of years. More massive stars, however, burn through their fuel much more quickly, shining brighter but living shorter lives. The size of a star largely determines its fate. Low-mass stars, like red dwarfs, burn their fuel very slowly and can live for tens of billions or even trillions of years. Since the universe is only about 13.8 billion years old, no red dwarf has yet died, meaning that the ultimate fate of these stars is still a mystery. Stars with masses similar to the Sun will eventually run out of hydrogen in their cores. When this happens, the core contracts and heats up, causing the outer layers of the star to expand. The star becomes a red giant, a much larger but cooler star. During the red giant phase, the core continues to shrink and heat up until it becomes hot enough to start fusing helium into heavier elements, such as carbon and oxygen. This phase doesn't last nearly as long as the main sequence phase, and eventually, the star sheds its outer layers, forming a beautiful glowing shell of gas known as a planetary nebula. What remains of the star is the core, now called a white dwarf, a dense, hot remnant that slowly cools and fades over time. Massive stars, on the other hand, experience a much more dramatic end. Stars with at least 8 times the mass of the Sun can fuse elements, all the way up to iron in their cores. However, once a star's core is composed of iron, fusion can no longer release energy. Iron is the most stable element, and rather than producing energy, fusing iron requires an input of energy. Without the outward pressure provided by fusion, the core of the star collapses under its own gravity, triggering a supernova explosion. A supernova is one of the most violent events in the universe, releasing more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. The explosion blasts the outer layers of the star into space, enriching the surrounding environment with heavy elements that can later be incorporated into new stars and planets. Supernovae are also responsible for creating the elements heavier than iron, such as gold and uranium, through a process known as neutron capture. What remains after a supernova depends on the mass of the original star. If the core is less than about 3 times the mass of the Sun, it becomes a neutron star, an incredibly dense object composed almost entirely of neutrons. Neutron stars are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. If the core is more massive than this, however, the collapse continues until the star becomes a black hole, a region of space where gravity is so strong that not even light can escape. The discovery of black holes and neutron stars has revolutionized our understanding of the universe, offering new insights into the most extreme conditions possible. For example, studying the behavior of matter and energy near black holes has provided crucial tests for Einstein's theory of general relativity, which describes how gravity works on large scales. Neutron stars, with their incredibly strong magnetic fields and rapid rotation, are also fascinating laboratories for studying the physics of matter under extreme conditions. In recent years, the study of these exotic objects has been further revolutionized by the detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects like merging neutron stars or black holes. The first detection of gravitational waves from a neutron star merger in 2017 provided astronomers with a wealth of information, including direct evidence that these mergers produce heavy elements like gold and platinum. Stars, through their life cycles, play a crucial role in shaping the universe. Their deaths create the elements that make up planets and living organisms, and their explosive ends can trigger the formation of new stars. Even the darkest and most mysterious objects in the universe, black holes, are born from the deaths of massive stars. In modern times, stars have continued to inspire scientific discovery. The study of starlight, for example, has led to some of the most profound discoveries in physics and astronomy. By analyzing the light from distant stars, astronomers can determine their temperature, composition, and distance. The discovery that the universe is expanding, for instance, came from observations of the light from distant galaxies, which showed that they are moving away from us at speeds proportional to their distance. The study of stars has also led to the discovery of the fundamental forces that govern the universe, from gravity to electromagnetism to nuclear forces. The fusion reactions that power stars provided the first clues to the nature of the strong nuclear force, one of the four fundamental forces of nature. Similarly, the study of the orbits of stars around the center of the Milky Way provided the first evidence for the existence of dark matter, a mysterious substance that makes up about 85% of the matter in the universe but interacts with regular matter only through gravity. Stars have also helped us understand the history and future of the universe. By studying the oldest stars, astronomers can determine the age of the universe and learn about the conditions that existed shortly after the Big Bang. Observations of distant galaxies have shown that the universe is expanding at an accelerating rate, leading to the discovery of dark energy, a mysterious force that is driving the acceleration. As we continue to study stars and their role in the universe, we are constantly reminded of our own connection to the cosmos. The elements that make up our bodies were forged in the hearts of stars that lived and died billions of years ago. The light we see from distant stars has traveled across vast stretches of space and time to reach our eyes, providing a glimpse into the distant past. In many ways, stars are a bridge between the very small and the very large. They are powered by the fusion of tiny atomic nuclei, yet they shape the structure and evolution of entire galaxies. Their light reveals the fundamental forces of nature, and their deaths create the elements that make life possible. Stars are not just objects to be studied, they are a reminder of the deep connections that link us to the universe as a whole. As our understanding of stars continues to evolve, we are constantly finding new questions to explore. What happens to the material that falls into a black hole? How do stars form in the early universe, when there were no heavy elements? How do magnetic fields influence the behavior of stars and the planets that orbit them? These are just a few of the mysteries that astronomers are working to unravel as they continue to study the stars. The study of stars is not just about the stars themselves, but also about the environments they inhabit and the impact they have on the broader cosmos. Stars are often born in clusters within dense molecular clouds, and their intense radiation can shape the surrounding interstellar medium, triggering further star formation or, in some cases, halting it. This interplay between stars and their environments is a key driver of galaxy evolution, creating the diverse structures and phenomena we observe in the universe. One of the most striking features of the universe is the way galaxies, stars, and planets are arranged in a seemingly ordered fashion. Galaxies are home to billions or even trillions of stars, all bound together by gravity. Within these galaxies, stars are not distributed randomly but often found in groups, clusters, or along the spiral arms of galaxies like the Milky Way. The patterns we observe in these structures are the result of billions of years of gravitational interactions, star formation, and stellar evolution. Spiral galaxies, such as our own Milky Way, are characterized by their bright, swirling arms, which are regions of active star formation. These arms contain giant molecular clouds, where new stars are being born, as well as older stars that have already evolved. The spiral structure itself is thought to be the result of density waves, areas of higher concentration of gas and dust that move through the galaxy, triggering star formation as they go. The oldest stars in spiral galaxies are found in the central bulge and the halo, regions that are relatively devoid of gas and have little new star formation. Elliptical galaxies, on the other hand, are typically older and more evolved than spiral galaxies. They contain mostly older stars and have very little gas or dust, meaning that star formation has largely ceased. The stars in elliptical galaxies are distributed in a more uniform, spherical shape, and the lack of gas means that these galaxies appear redder than their spiral counterparts. Elliptical galaxies are often found in galaxy clusters, where interactions with other galaxies can strip away the gas and prevent further star formation. The largest galaxies in the universe, known as supergiant ellipticals, are often found at the centers of galaxy clusters. These galaxies can contain hundreds of billions of stars, and their central regions are thought to harbor supermassive black holes with masses millions or billions of times that of the Sun. The presence of these black holes can have a profound effect on the galaxy, as the energy released by matter falling into the black hole can heat up the surrounding gas, preventing it from cooling and forming new stars. Dwarf galaxies, which are much smaller than spiral or elliptical galaxies, often contain only a few billion stars. These galaxies are thought to be the building blocks of larger galaxies, and many of them are found orbiting larger galaxies like the Milky Way. Dwarf galaxies can be irregular in shape, and they often contain younger, bluer stars. Some dwarf galaxies are undergoing bursts of star formation, while others, like dwarf ellipticals, have long since ceased forming new stars. Stars also play a key role in the formation and evolution of planets. The planets in our solar system, for example, formed from the leftover gas and dust that surrounded the Sun in its early stages. This material coalesced to form planetesimals, which eventually grew into the planets we see today. The chemical composition of the planets reflects the material from which they formed, which in turn was enriched by the earlier generations of stars that lived and died before the Sun. The discovery of exoplanets, planets orbiting stars other than the Sun, has opened up a new frontier in the study of stars and their planetary systems. To date, thousands of exoplanets have been discovered, ranging from gas giants like Jupiter to small, rocky planets similar to Earth. The study of exoplanets has revealed a surprising diversity of planetary systems, some of which are very different from our own. For example, some stars have hot Jupiters, giant gas planets that orbit very close to their host stars, while others have planets in orbits that are much more eccentric than the nearly circular orbits of the planets in our solar system. The search for potentially habitable exoplanets has focused on planets that orbit within the habitable zone of their host stars, the region where conditions might be right for liquid water to exist. While many of the planets discovered so far are too hot or too cold to support life as we know it, the discovery of Earth-sized planets in the habitable zones of their stars has raised the exciting possibility that there may be other worlds out there with the right conditions for life. The study of stars and exoplanets has also led to the discovery of new types of stars and stellar phenomena. For example, astronomers have discovered pulsars, which are rapidly rotating neutron stars that emit beams of radiation. These beams sweep across the sky like the beams of a lighthouse, and if they happen to sweep across Earth, we see them as regular pulses of radiation. Pulsars are incredibly precise cosmic clocks, and studying their behavior has led to new insights into the nature of matter under extreme conditions. Another fascinating type of star is the magnetar, a type of neutron star with an incredibly strong magnetic field. The magnetic fields of magnetars are so intense that they can distort atoms and create bursts of high-energy radiation. These bursts, known as gamma ray bursts, are some of the most energetic events in the universe, releasing more energy in a few seconds than the Sun will produce in its entire lifetime. The discovery of these exotic stars has expanded our understanding of the diverse ways in which stars can evolve and die. While most stars, like the Sun, end their lives as white dwarfs, some stars end in spectacular explosions that leave behind neutron stars or black holes. These stellar remnants are some of the most extreme objects in the universe, and they provide unique opportunities to study the laws of physics under conditions that cannot be replicated on Earth. Stars also play a central role in the study of cosmology, the science of the origin and evolution of the universe. By studying the light from distant stars and galaxies, astronomers have been able to piece together a detailed picture of how the universe has evolved over the past 13.8 billion years. One of the key discoveries of cosmology is that the universe is expanding, with galaxies moving away from each other at speeds proportional to their distance. This discovery, made in the 1920s, led to the development of the Big Bang theory, which describes how the universe began as a hot, dense state and has been expanding ever since. The study of the oldest stars has provided key insights into the early history of the universe. By measuring the ages of the oldest stars, astronomers can determine when the first stars formed and how the first galaxies assembled. These early stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, as the heavier elements had not yet been created. The deaths of these first stars, in supernova explosions, enriched the universe with heavier elements, paving the way for the formation of planets and life. Stars have also played a crucial role in the discovery of dark matter, a mysterious substance that makes up about 85% of the matter in the universe. Dark matter does not emit, absorb, or reflect light, so it cannot be seen directly. However, its presence can be inferred from its gravitational effects on stars and galaxies. For example, the rotation curves of galaxies, how fast the stars and gas in a galaxy are orbiting the center, indicate that there is much more mass in the galaxy than we can see. This unseen mass is thought to be dark matter. The nature of dark matter is one of the biggest mysteries in astrophysics. While we know that dark matter exists from its gravitational effects, we still don't know what it is made of. Several theories have been proposed, including the idea that dark matter could be composed of as yet undiscovered particles, but so far, no direct evidence for these particles has been found. Stars have also played a role in the discovery of dark energy, a mysterious force that is causing the expansion of the universe to accelerate. This discovery, made in the late 1990s, was based on observations of distant supernovae. By measuring the brightness of these exploding stars, astronomers were able to determine how fast the universe was expanding at different times in its history. To their surprise, they found that the expansion of the universe was not slowing down, as expected, but speeding up. This discovery has led to the development of new theories about the nature of the universe and its ultimate fate. As we continue to study stars and their role in the universe, we are constantly reminded of how much we still have to learn. From the formation of the first stars to the ultimate fate of the universe, stars are at the center of some of the biggest questions in science. They are the engines of cosmic evolution, creating the elements that make life possible and driving the formation of galaxies and planets. At the same time, they are also some of the most beautiful and awe-inspiring objects in the universe, lighting up the night sky and providing a glimpse into the vastness of space and time. The role of stars in the cosmic web extends beyond just the formation of elements, galaxies, and planetary systems. Stars also play a pivotal role in the large-scale structure of the universe, influencing the formation of galaxy clusters and superclusters, the largest gravitationally bound structures in the cosmos. These immense formations are woven together by filaments of dark matter and gas, forming a cosmic web that spans the entire observable universe. In the early universe, shortly after the Big Bang, the distribution of matter was relatively uniform, with tiny fluctuations in density caused by quantum fluctuations during the inflationary period. Over time, gravity amplified these fluctuations, causing regions of higher density to collapse and form the first stars, galaxies, and galaxy clusters. The first stars, or population 3 stars, were massive, short-lived, and responsible for the ionization of the early universe during the epoch of reionization. Their deaths in supernova explosions enriched the surrounding gas with heavier elements, allowing for the formation of the next generation of stars and galaxies. The process of star formation is intricately linked to the large-scale structure of the universe. As galaxies form and evolve, their stars emit radiation and eject material into the surrounding interstellar medium, influencing the behavior of gas and dark matter in the galaxy's halo. Feedback from supernova explosions and active galactic nuclei, AGN, can regulate the rate of star formation, preventing galaxies from forming too many stars too quickly and allowing them to maintain a delicate balance between gas inflows and outflows. Galaxies are not isolated entities. They are part of larger structures such as groups, clusters, and superclusters. In these environments, interactions between galaxies, such as mergers and tidal forces, can trigger bursts of star formation or strip gas from galaxies, effectively quenching star formation. These interactions play a crucial role in shaping the morphology of galaxies, transforming spirals into ellipticals, and regulating the growth of galaxies over time. One of the most important mechanisms by which galaxies grow is through mergers, where two or more galaxies collide and coalesce into a single, larger galaxy. When galaxies merge, their stars and gas clouds interact in complex ways, leading to intense bursts of star formation known as starbursts. These events can produce hundreds or thousands of new stars in a relatively short period of time, drastically altering the appearance and structure of the galaxy. Mergers also funnel gas into the central regions of galaxies, potentially fueling the growth of supermassive black holes at their cores. Supermassive black holes are thought to reside at the centers of most, if not all, large galaxies. These black holes can have masses ranging from millions to billions of times that of the Sun, and can have a profound impact on their host galaxies. When material falls into a supermassive black hole, it forms an accretion disk that heats up and emits large amounts of radiation, sometimes outshining the entire galaxy. This process, known as an active galactic nucleus, AGN, can produce powerful jets of relativistic particles that shoot out from the black hole's poles, affecting the surrounding gas and suppressing star formation. AGN feedback is thought to be one of the key processes that regulate galaxy growth and evolution. By heating up the gas in the galaxy's halo, AGN can prevent it from cooling and forming new stars, effectively quenching the galaxy and halting star formation. This feedback mechanism is particularly important in massive galaxies, where it helps to explain why many of the most massive galaxies are observed to be red and dead, with little ongoing star formation. The interaction between stars, galaxies, and the cosmic web is a dynamic and ongoing process. As galaxies move through the cosmic web, they interact with the surrounding dark matter and gas, accreting material and growing over time. At the same time, feedback from stars and black holes regulates the amount of gas available for star formation, shaping the evolution of galaxies on cosmic timescales. Stars also play a role in the enrichment of the intergalactic medium, the diffuse gas that fills the space between galaxies. When stars die in supernova explosions, they eject heavy elements into space, enriching the surrounding gas with metals. This process, known as chemical enrichment, is responsible for the gradual buildup of heavier elements in the universe over time. These metals are important for the formation of planets and life, as they are the building blocks of complex molecules and structures. The study of the intergalactic medium has revealed that it is not a uniform, featureless void but rather a complex and dynamic environment shaped by the ongoing processes of star formation, galaxy evolution, and feedback. Observations of the intergalactic medium have provided valuable insights into the distribution of matter in the universe, the growth of large-scale structure, and the role of feedback in regulating galaxy formation. One of the most intriguing aspects of stars is their ability to act as cosmic time capsules, preserving a record of the history of the universe. By studying the chemical composition of stars, astronomers can trace the history of star formation, chemical enrichment, and galaxy evolution over billions of years. Stars that formed early in the history of the universe, for example, have lower metallicities than younger stars, reflecting the fact that there were fewer heavy elements available in the early universe. These metal Stars, found in the halos of galaxies and in globular clusters, are some of the oldest objects in the universe, and their study has provided important clues about the conditions in the early universe and the formation of the first galaxies. The ages of the oldest stars provide a lower limit on the age of the universe, helping to constrain models of cosmic evolution and the timing of key events such as the formation of the first galaxies and the reionization of the universe. The study of stars has also led to important discoveries about the nature of dark matter, the mysterious substance that makes up the majority of the mass in the universe. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence can be inferred from its gravitational effects on stars and galaxies. For example, the rotation curves of galaxies, which show how fast stars and gas are orbiting the center of the galaxy, suggest that there is much more mass in the galaxy than can be accounted for by the visible stars and gas. This unseen mass is thought to be dark matter. Dark matter is also thought to play a crucial role in the formation of galaxies and large-scale structure. Simulations of galaxy formation suggest that dark matter forms a scaffold around which galaxies and galaxy clusters form. As galaxies grow and evolve, they are influenced by the gravitational pull of dark matter, which helps to shape the distribution of stars and gas in the galaxy. The nature of dark matter is still one of the biggest mysteries in astrophysics, and understanding its role in the formation and evolution of galaxies is a key goal of modern astronomy. Stars have also been instrumental in the discovery of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Observations of distant Type I supernovae, a type of exploding star, revealed that the universe is expanding faster than expected, suggesting the presence of a previously unknown form of energy. This discovery, made in the late 1990s, has led to a revolution in our understanding of the universe and its ultimate fate. Dark energy is thought to make up about 70% of the total energy density of the universe, and its discovery has raised profound questions about the nature of the cosmos. Is dark energy constant, or does it change over time? Will the universe continue to expand forever, or will it eventually slow down and collapse? These questions are at the forefront of modern cosmology, and the study of stars and their explosions continues to play a crucial role in unraveling the mysteries of dark energy and the fate of the universe. Stars have shaped not only the universe but also human civilization. For millennia, humans have looked to the stars for navigation, timekeeping, and inspiration. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.